All right, I think we can get started. So, hello and welcome and happy holidays. This is our last seminar this year, please come back in we will be back in January. So I'm John, the seminar coordinator, and together with me is Miss Kathy Manley, and she's our communication specialist. And Kathy and I will be today's moderator. Today, we are excited to have our distinguished speaker, Professor James Smith, joining us from Princeton University. Just so you know, then the seminar is being recorded and will be later published on our YouTube channel. Please feel free to ask questions. You can do this through chat and text us a message, or you can raise up your virtual hands and we will unmute you. Let me give a brief introduction about our speaker today. So Professor James Smith is a William and Edna McNear Professor of Engineering at Princeton University. He received his BS in Mathematics from the University of Georgia and his PhD in Environmental Engineering from the Johns Hopkins University. So Professor Smith's research interests is focused on the hydrology and hydrometeorology of extreme floods. He has received numerous awards. He is a fellow of the AGU, AMS, and receives the Hydrologic Science Medal of AMS. Let's welcome the speaker, and I will give the ball to the speaker. So Professor, please proceed.
Thanks, John. So how hard can it rain in the mid-Atlantic? I'm going to spend much of the presentation using the Ellicott City storm of May 27th, 2018 to examine the question, but I wanted to begin by giving, let's see, there we go. By giving a background on rainfall extremes in the mid-Atlantic. The largest 1-minute rainfall in the US and in the world occurred about 30 kilometers west of Baltimore and Unionville, Maryland in July of 1956. Not a lot known about the storm. One of the observations is that it was embedded in a large area of intense convection with tornadoes reported in the region. Now moving into Baltimore, a record of more than 120 years, the record rainfall rates for Baltimore at 5, 15, and 30 minutes come from a storm in July of 1903. It produced tornadoes as well as devastating flooding. The report from the Sun the day after the storm describes in vivid detail the storm. One of the interesting things that notes about the storm is that this merger of two elements was a distinctive feature of the storm, and we'll come back to that. So this is part of the history. The Mid-Atlantic has seen some of the largest rainfall rates at short time intervals of anywhere in the world, including the Unionville storm, and so they provide context for the questions that we'll be looking at. The questions specifically deal with identifying the physical mechanisms that are associated with extreme rainfall for short durations and for small spatial scales. And so roughly 1 minute to 3 hours and roughly 1 to 100 square kilometers. Concerned with and focus on 3 elements. One is looking at an individual convective cell and how does it rain hard from an individual convective cell. And then the organization of convective cells and the production of rainfall over timescales that are longer than the life cycle of a single convective cell are also important parts of the problem. Storm environment, we'll look at it from a variety of guises. I'll point just briefly to the climate change questions, certainly from the Ellicott City storms. If your municipal regions in the and the region, one of the big concerns is whether these types of storms are increasing in a warming climate. And so we'll talk just a brief bit about the climate change aspects of the storms. One of the climate change question has received quite a bit of attention. One that hasn't received nearly as much attention, but perhaps should, is how the frequency of these extreme rain rate events vary over the region. So that'll be on the docket. And then finally, in thinking about extremes of rainfall, one possibility is that all of these in-member events are really unique. And that plays into a variety of the questions, including those associated with sorting out what's taking place in a warming environment. Now, like the two storms, the July 1956 and the July 1903 storm, we'll wonder whether it's the most intense thunderstorms that dominate the upper tail of rain rates. It's kind of a contentious notion. There's certainly textbooks that point to the most intense convection as unlikely candidates for being extreme rainfall producers, largely revolving around sort of water balance notions and precipitation efficiency. But we're going to start from the perspective that it really is the most extreme events on the convective intensity spectrum that are dominating extreme short duration, small area rainfall. Now, it's going to be a purely empirical look at cloudbursts, and so it'll focus on the May 27th, 2018 Ellicott City storm. And then there are 10 other cloudbursts during the period from 2012 to 2020. And these we've identified as during this period, these are the most extreme storms in terms of short duration, small area rainfall in this 9-year window. It's hard to sort out what these events are in reality. And we're using a variety of different types of information to pick out these most intense cloudbursts. One, we're using stream gauging observations. And so what you see here in this figure is a representation of the most extreme measured flood peaks in the mid-Atlantic region from the U.S. Geological Survey. The lines here, this is drainage area versus peak discharge, and the red, blue, and black lines are reflecting envelope curves of flood peak magnitudes. The red line is for 1,000 cubic feet per second per square mile, long viewed as one of the upper bounds. We've sort of passed that. The blue line is 2,000 and the black line is 4,000. Now, the red diamonds that you see here, the most extreme floods that have ever been measured in the mid-Atlantic region are the Ellicott City storms from May of 2018. These are scales from 2 to 4 square kilometers. The black diamonds are the July 2016 Ellicott City storm, so they certainly appear here. There are 3 other events that we're looking at in this list of 10 or list of 11 that come from stream gauging observations. The big white circle is a storm in Little Catoctin Creek along the eastern margin of the Blue Ridge that occurred less than 2 weeks before the May 2018 Ellicott City storm. The blue squares that you see are from the July 18th, 1942 Smethport storm that produced world record rainfall of close to 800 millimeters in between 4 and 5 hours, 10-minute rain rates exceeding 1,000 millimeters per hour. And so Little Catoctin Creek flood of May 15th, 2018 is right up with the Smethport storms. So these are one way that we identify extreme events. We use rainfall measurements both from radar and rain gauge to identify the other events. The Ellicott City storms, based on NOAA precipitation frequency analyses, have rainfall accumulations that exceed 1,000-year return intervals at various durations. And for these events that we're looking at here, they typically are going to, if they're identified based on rainfall, they typically have rainfall accumulations at 5 minutes to 3 hours that are on the 1,000-year return interval or longer event. So these are truly exceptional events that we're looking at. So it's these 5 events, 2012 to 2020 is picked because we're principally going to base our analyses on polarimetric radar measurements from the Sterling, Virginia WSR 88D radar operated by the National Weather Service. So polarimetric measurements are a big part of the analyses. The 3 measurements we'll focus on are reflectivity, differential reflectivity, and specific differential phase shift, or KDP. Shown here, this is for the Ellicott City storm 2017 UTC on May 27th. We have 3D pictures, representations of the storm. From these observations, we obtain information about kinematics, and I'm principally thinking of updrafts and downdrafts here. Microphysics, not just drop size distributions, but also composition in terms of rain, snow, hail, and graupel. The 3 types of measurements, differential reflectivity is largely related to the size of hydrometeors, and specific differential phase shift to the liquid water content. And so what we've done is we've largely taken material that's been developed in the tornado community to examine updrafts, downdrafts, microphysics, and then close to the surface, the occurrence of heavy rainfall. So the 2012-2020 time period comes about because analyses building on the supercell literature for tornadoes are really going to play a central role in assessing how hard it can rain and how it rains hard. Rainfall will come both from polarimetric radar and from rain gauge observations. Now, the convective intensity question, there are a variety of ways of looking at it. We'll use observations from the National Lightning Detection Network as kind of a systematic way of looking at convective intensity. In the 5-kilometer images here, you can see the white crosses are, they're actually intra-cloud flashes in a 5-minute window associated with the radar measurement. And then finally, we'll use reanalysis fields to derive environmental variables characterizing the storm environment. Now, a bit of a spoiler alert. This is 2017 UTC, and most of the information that's needed to explain the largest flood peak in the mid-Atlantic is present in this time period. We really got all the key ingredients that are associated with the peak discharge and the New Cut Branch tributary of Tiber Run here. Now, taking a closer look at the May 27th storm, the figures on the left are just 2 versions of storm total rainfall. In the top figure, you can see the Tiber Branch watershed. It's 3 tributaries: Hudson Branch, the main stem of Tiber Branch, and New Cut Branch that drain through downtown Ellicott City. Rainfall accumulations peak in the lower portion and New Cut, and then we have peak rainfall accumulations extending to the east into Catonsville, Maryland. The bottom figure shows the NOAA precipitation frequency results. At 3-hour time scale, rainfall accumulations exceeded 1,000-year return intervals over more than 100 square kilometers. So a truly extreme event. New Cut Branch has a drainage area of 4 square kilometers. The entire Tiber Branch is 10 square kilometers. You see the basin average rain rates for the 3 tributaries on the right. We've got pulses of rain or storm elements, 19 to 20 UTC, 20 to 21, and 21 to 22. And it's really going to be this 20 to 21 UTC period in New Cut Branch. We know that that's what produces this envelope curve flood peak. But we've got large variability in time and space, and we've got multiple convective elements that are contributing to extreme rainfall over the Tiber Branch watershed and east into Catonsville, Maryland. Now, environmental variables, the bottom right figure here shows 850 hectopascal temperature and wind fields from the North American Regional Reanalysis right as the storms are kicking off at 21 UTC. We derive a variety, and this is the sort of standard set of variables that we look at for storm environment. The precipitable water of 52 millimeters was a record for May. 52 is large over the year, but it's certainly not a record for the location. IVT is the magnitude of the vertically integrated water vapor flux. 260 kilograms per second per meter is large, but not extreme. The convective available potential energy at 2230 joules per kilogram is large. Cloud base is very low. The 0 degree level is around 4 kilometers, so a warm cloud depth of about 4 kilometers. And the steering winds from 850 to 500 millibars that are advecting storms along are west to east at about 10 meters per second. Now, mesoscale structure differs for all of these storms, and I'll point, if you look at the figure in the bottom right, there's a convergence zone that's associated with a frontal boundary that extends east-west through the northern tier of Maryland. At 20 UTC in the reflectivity image, you can see convection developing over this convergence zone. Ellicott City is highlighted. In this line of convection, there are a number of convective elements, including the one that passed over from 19 to 20 UTC. Part of the storm environment is rapidly increasing precipitable water. The upper figure shows that precipitable water increases from 48 millimeters at 12 UTC to above between 52 and 54 millimeters in this critical period of extreme rainfall. So these are aspects of the storm environment. Looking at the rainfall and the convective intensity piece from lightning, it's just on the upper end of the convective intensity spectrum. From any perspective that you look at, more than 25 lightning strikes per square kilometer is large for this region. Both the lightning map and the rainfall map, BC 23 is the location of a rain gauge operated by Baltimore County that had 200 millimeter rainfall accumulation. The time series shows lightning counts in a 5 kilometer region around the rain gauge location. Again, that's 19 to 20, 20 to 21, 21 to 22 period of intense convection. In the top figure, the rain gauge observations from BC 23 and then the polarimetric radar measurements. There are two ways of looking at this. One, it's very important to be able to measure rainfall accurately from radar. And there are some serious issues associated with that. Molly Cheney is looking at estimating extreme rainfall from radar and developing the best ways of using polarimetric measurements to estimate rainfall. And so that's a key aspect of looking at extreme rainfall. The flip side of it is it gives us information on what's taking place with the storm. One common problem with radar measurements of rainfall is that we're taking a snapshot and any rainfall algorithm implicitly assumes some form of terminal velocity. And in reality, what's going on is you can often have very strong downdrafts, and we'll see that's an important feature of the extreme rainfall story. So underestimation is going to be a signature either of anomalous drop size distributions or of very large downdrafts, and both, I think, play an important role in producing extreme rainfall from these storms. Now, taking a look at the evolution of the storm prior to the period of peak rainfall, this is the picture at 2017 UTC from polarimetric radar measurements. ZDR columns are regions of elevated differential reflectivity that extend above the 0 degree level 0-degree level is about 4 kilometers above ground level. The most striking feature of this storm is the size of the updraft at 2017 UTC. This would be a very, very large updraft, even for a tornadic supercell. So in the 5-kilometer observation, this updraft signature is really what drives extreme rainfall. Now, the downdraft is kind of comparably extreme. Wind shear plays an important role in transferring condensate from the updraft into the downdraft, and this west-east oriented downdraft is going to play out as the dominant feature in extreme rainfall. Now, another element is that in the reflectivity, differential reflectivity, and KDP measurements, we have signatures of microphysical type. And particularly at 3-kilometer, what we're looking at is melting hail with rain. And there's several aspects of that. One important aspect is that for negative buoyancy and downdraft, melting hail is going to be an important contribution to downward vertical motion. Now, heavy rainfall is already occurring. The 2 black squares, one is Ellicott City, one is BC 23. And so at this period at 2017, we're getting extreme rainfall. Now, over the next 15 minutes, we go from weakening updraft, strengthening downdraft. At 3 kilometers, this tremendous growth in this region of melting hail with rain, rainfall at the surface becoming more extreme. And then over the next 10 minutes, cloudburst rainfall extending from Newcut Branch into Catonsville in the BC 23 location. So this is the life cycle of the convective element that's responsible for the largest flood peak measurement in the Mid-Atlantic region, that at Newcut Branch. So that's the perspective looking as this developed. There's one other kind of key feature associated with this, and that is looking back from 2017 to 2012 UTC. What we see is there are actually 2 cells. We see this both in the reflectivity, in the ZDR, we see the updraft signatures, and in the KDP, we see the downdraft signatures. So over a 5-minute time period, we went from these 2 distinct, very, very intense convective elements to 2017, where we have this updraft feature that is one of the key elements of producing the extreme rainfall at the surface. So cell merger, something that's been looked at for going back to Joanne Simpson's studies when she was at NASA in the 1980s, has been identified as one of the elements that contributes to extreme convection, and in this case, it's a big player in looking at extreme rainfall. The figure here shows the 2 cells from 2002 UTC. Treating cell 1 is going from 20 UTC to 2041. 2017 is the time of merger, and so we can see the 2 cells evolving. They're pretty much moving with the steering winds, this 10 meter per second steering winds up until cell merger, and then they're basically just stuck over a Newcut Branch for a period of about 20 minutes. So this convective evolution was a key element of extreme rainfall. And so as we think about how we produce record rainfall and flood peaks, maximizing the updraft mass flux is certainly one element. And there, in this case, it's the cell merger process that sort of translated the storms into the most extreme phase. Wind shear is important and a key aspect of not just transporting hydrometeors to the downdraft, but determining the structure of the downdraft. And then in terms of the downward vertical motion, melting hail is an important piece of producing negative buoyancy and having tremendous downdrafts that are associated with extreme rainfall. And then this anomalous interaction of cells plays an important role in cell merger. So these are key ingredients, especially for the 20 to 21 UTC storm, but similar elements played out for the 19 to 20 UTC, and similar elements played out to the east over Dundalk, where there are comparably extreme short-term rain rates. So this convective life cycle is kind of a characteristic piece of extreme rainfall from the May 27th, 2018 storm. Now, one of the questions that arises then in looking at these events is whether this is really a kind of characteristic of cloudbursts in general. One of the sort of disconcerting features is that the first Ellicott City storm, although the rainfall distribution is quite similar, also 1,000-year return interval rainfall, here at time intervals ranging from 15 minutes to the 180 minutes, like the May 27th storm. But from there, there are pretty significant differences between the 2016 Ellicott City storm and the May 2018 storm, where the 2018 storm is really at the top end of the convective intensity spectrum. The July 2016 storm has lightning, but it's on the weak end of the convective intensity spectrum. There's actually more intense convection to the east with heavy rainfall over Baltimore City. Now, there's the mesoscale structure piece, and the mesoscale evolution here is very different from the May 27th, 2018 storm. The thing that's really distinctive about the July 2016 storm is the vertically integrated water vapor transport. It's just, it's really at the peak for all of these cloudbursts. And not only is it a peak, but it's changing rapidly over time, and it matches the peak in rainfall that we see at the Ellicott City rain gauge below, where we have 200 millimeter per hour rain rates at 0 UTC on July 31st. So the Ellicott City, the 2016 storm, it was right in with May 2018 in terms of precipitable water. It was a little higher at 55 millimeters. In terms of vertically integrated water vapor flux, it was quite different. In terms of mesoscale's structure and evolution, it's quite different. So it does raise the question of whether all cloudbursts are unique, and looking at the 10 storms and sort of carrying out the same types of analyses for those storms as we've done for the May 2018 storm. The answer is yes, but there's plenty of structure associated with the results that we see, and they sort of tie into convective intensity, convective evolution, and atmospheric water balance pieces. Convective evolution, I'm principally thinking in terms of this cycle that we saw for the May 2018 storm, where we have tremendous updraft mass flux and negative buoyancy producing extreme rain rates at the surface. The atmospheric water balance in general, it's high precipitable water events and large water vapor transport can help with these storms. Now, the other question that comes up is whether the most intense thunderstorms dominate the upper tail of rainfall rates. And the basic answer to that question is a wishy-washy yes. July 2016, sort of on the weekend, but most of the storms are kind of up there with the May 2018 storm in a variety of measures of convective intensity, including those that we used with the lighting measurements. Now, one part of sort of worrying about whether all storms are unique is the question that the Baltimore City Department of Public Works wants to know is whether these types of storms are increasing in frequency in a warming climate. And it's sort of it's the biggest question that water managers worry about in terms of rainfall extremes. The atmospheric environment variables provides one way of kind of trying to get at those questions, and the atmospheric water balance elements are kind of the most natural thing to look at. Now, Yibing Su has been looking at atmospheric water balance trends. These are analyses based on 40 years of North American regional reanalysis fields, and it's just looking at trends in annual maximum precipitable water. There are large and significant trends over the last 40 years in the NAR precipitable water fields. It translates to about 1 millimeter per decade in the mid-Atlantic. Yibing's looked at similar analyses for things like exceedance of 45 millimeters. How often does that occur? And we're seeing similar increases there. And I'll point out variables like CAPE see similar increases in the mid-Atlantic. And so one sort of simple way of looking at the climate change is that we are tossing the dice more often. These atmospheric water balance components, they're really blunt instruments. They don't really tell us how extreme rainfall is occurring, but they do provide key elements of the environment. And that may be the best that we can do at this point in assessing the potential for increasing frequency of these really high-end events. Now, so the climate change piece is certainly one that that rightly occupies a great deal of interest, both around the world, the United States, and then locally in the Mid-Atlantic region. One that hasn't received nearly as much attention, and here too it would be locally, nationally, and around the world, is spatial heterogeneities that are associated with cloudburst rainfall. And so that's one piece of the extreme rainfall picture that we've been looking at closely. And these are just two types of analyses. Sort of one question is thunderstorm frequency, does it vary over the Mid-Atlantic region? And the answer is yes, it varies quite a bit. We see this area of elevated lightning flash density extending from southwest of Washington, D.C., northeast of Baltimore City, with a maximum located in Baltimore, east and northeast of Baltimore. In looking at rainfall analyses, and the figure on the left is based on a 21-year record, rainfall record for the region derived from radar rainfall measurements. And here we're looking at sort of a funny measure of extreme rainfall. We're looking at the mean annual rainfall that's produced by 15-minute rain rates that are larger than 50 millimeters per hour. And we see this northeast maximum. It's quite a striking feature northeast of Baltimore and just to the west of Chesapeake Bay. We've carried out numerical experiments, principally Yonghee Ryu, and the interaction of the Bay Breeze circulation and the urban heat island circulation is an important player in this northeastern maximum and rainfall. And so what we see is that over the region, there really are large spatial gradients and thunderstorm occurrence of extreme rainfall They're tied to urban impacts on convective rainfall, land water boundaries, especially associated with Chesapeake Bay, and as we move to the west, associated with orographic mechanisms. And by many metrics, they're large compared to the climate change signals that we're looking for in extreme rainfall. So that's one element that's important. And looking at this collection of 10 events that we've examined, I wanted to just highlight a few of the other issues that come up that are sort of tied to features of convective evolution that we saw for the May 2018 storm. Some of these issues associated with spatial heterogeneity, the question of whether it really is the most convectively intense storms. I want to give you more of a sense for what analyses of these other storms show. And I'll start with this other May 2018 storm that it produced an envelope curve flood peak in Little Catoctin Creek. The figures here show rainfall on the left and lightning flash density on the right. In the lightning image, you also see it's the Blue Ridge. The Blue Ridge is kind of divided up into two separate ridges in the western margin of the Maryland Piedmont, Catoctin Mountain to the east and South Mountain to the west. And the thing that we see, a very striking feature of this storm, is that we get peak convective intensity just on the east slope of these two ridges. And the rainfall, it's principally on the South Mountain side that we have the most extreme rainfall. The three basins that are shown in the rainfall figure include Little Catoctin Creek, which is the smallest one, a tributary of Catoctin Creek, and then Israel Creek to the west. The things that are kind of common to the May 2018 storm, the May 27th, 2018 Ellicott City storm, this storm is the mesoscale structure is really, really similar. We have an east-west oriented frontal boundary that's really organizing convective evolution over the course of the day. The convective life cycle, over and over, we repeatedly see the same types of features with these very pronounced updraft signatures and ZDR columns and downdraft signatures in KDP columns. So in many respects, this storm is similar to the May 27th, 2018. It is at the very high end of the convective intensity spectrum on all measures, higher than the May 27th, 2018 storm. The orographic convection piece is, I think, an important and unique aspect of the storm. It's on the low end of precipitable water with 42 millimeters. And so we can produce extreme rainfall without being in this 50 plus millimeter regime. The strength of the updraft can overcome a little bit of a deficiency in terms of water vapor content. So these are some of the elements for this storm. There are actually many others that are interesting here. Also, on the very extreme end of the convective intensity spectrum is a storm that hit Baltimore City in August of 2019. Here, it's 1,000-year rainfall at 60-minute time interval. Again, the same convective life cycle with the same types of updraft, downdraft signatures for this particular storm. On the extreme end of convective intensity. Here, the piece that is distinctive is the urban impact on convective evolution. Also distinctive is this is the lowest precipitable water of any of the 11 events, and again, extreme convective intensity can overcome some deficiency in column water vapor content. So the August 2019 storm also ended with the two May 2018 storms, as is a storm in August of 2015 northeast of Baltimore. We have the record flood peak. This is one of the record flood peak events. And rainfall based on a combination of radar and rain gauge observations, 90-minute rainfall is 30% larger than 1,000-year return interval values. It's on the extreme end of the convective intensity spectrum, and it's also the same sorts of convective evolution that we saw for the May 27th, 2018 storm. And this is very much a northeast Baltimore event where we have interactions of the urban heat island and bay breeze circulation. It's a very distinctive mesoscale structure, different from the May 2018 storm. And then finally, just the one event that doesn't have any lightning is in June of 2017. It has 1,000-year rainfall accumulations at 30-minute time interval, 550 15-minute time interval. It's high on the precipitable water spectrum. One of the issues that's common to many of these events, and certainly to this one, is that errors in radar rainfall estimates are an important part of the story in assessing extremes of rainfall and developing enhanced tools for estimating extreme rainfall is an important feature of the analyses that we carry out. So this no lightning, weak convection is in with the July 2016 storm, and not being on the high end of the convective intensity spectrum. You can produce cloudburst rainfall without having extreme convection taking place. So what we see is this, yes, it is the most intense convective events that are most often at play. There are large differences in properties of the storms, but there are also important similarities. So the conclusion that all cloudbursts are unique, but that there are enough common features that we can proceed with a variety of important problems that tie into providing information on extreme rainfall and flooding hazards in urban areas. It is certainly important to focus on the most intense thunderstorms as agents of the most extreme rainfall. What we see from the May 2018 storm is we've got a model system for a convective life cycle, and exploring how that convective life cycle plays out in detail in other events is certainly an important feature in expanding our understanding of cloudburst rainfall. The underserved story is the one associated with spatial heterogeneities, complex terrain, urban impacts, land-water boundaries. There are prominent features here, and there are prominent features in many settings. The polarimetric measurements provide a critical tool for examining extreme rainfall. A big challenge is developing tools that allow us to estimate extreme rainfall at short duration and small spatial scales accurately from polarimetric measurements. And so basically, in looking at how hard can it rain, this is kind of beginning the process of trying to sort out how it rains hard. There's much to learn, but the key element is going to be sorting out how we produce rainfall like we've seen in these cloudburst events. And so with that, I'd be happy to answer any questions.
Thank you, Dr. Smith. So if any of our attendees have any questions, you could raise your virtual hand by expanding the attendee panel. There's a little hand button at the bottom of the panel, and I'll unmute people in the order that they raise their hand, or you can type your question in the chat, and I will read it out loud. Oh, we have one from Karen. Karen, you are unmuted. Karen, can you hear us?
I was able to unmute. Hi, Jim, this is Karen Prestgard.
Hi, Karen.
So my question has to do with your discussion of what makes these extreme, the most extreme ones that have the small spatial and temporal scales. And one of the things you said was that it didn't seem to be connected to warming trends or climate change. But I was thinking that when you were showing the diagrams of increasing temperatures and rainfall, etc., that's kind of an overprint, and then it's perhaps enhanced by these local things like the land water boundaries and the urban heat islands, etc. I wonder if you could comment on that, how the climate change and these special conditions might work together in the future.
Yeah. So in terms of the the spatial heterogeneities, the terrain and the land water boundaries are pretty much static. The urban piece, less so, and the expanding urban piece is certainly an important part. One of the elements I didn't go into is we've done numerical experiments for the May 27th, 2018 storm, and removing the city changes the form of convection. Is basically assisting with convergence along the west side of Baltimore. That was a piece of of even the May 27th, 2018 storm. So I think the urban piece is really an important one. It's changing some in the Baltimore-Washington corridor. Around the world, it's certainly changing very rapidly.
Thank you.
Thank you for that. We have a second question from Zawin Lee. You are now muted as well.
Can you hear me?
Yes.
Oh, thanks. I actually live in Ellicott City. Those storms flooded my basement. That's the most inconvenience. I have a small question about the people. So you're calling, when you are doing the storm evolution analysis, you use ZDR as a proxy for updraft and KDP as a proxy of downdraft. I sort of understand ZDR a lot of times are indication of large particles. So if they're pretty high, that so it's an updraft. Can you explain why you use ZDP as a proxy for downdraft? What's the physics behind that?
Let's see. So that goes to the ZDR piece, and so this ZDR column, KDP column, it encompasses a set of analyses that have been developed in the tornado literature. So the ZDR column, the sort of distinctive feature there is that you have large values of ZDR that extend above the 0 degree level. And that the interpretation is that you've got supercooled liquid water drops there and associated with really strong downdrafts. Now then the interpretation for the KDP as a downdraft signature has typically, it follows from the shear driven transport of hydrometeors from the updraft. And for the Ellicott City storms, we see this elongated region that is the transport region from the updraft that we're identifying as the downdraft structure. There's nothing that really says that the vertical velocities are negative there. It's really inferring them from the larger picture of ZDR, KDP, and the reflectivity field, especially sort of identifying where the hail cores are.
Okay, so you also added the horizontal wind, the wind structure in terms of identifying where the downdraft is. Yeah,
and that's not something that, that's really original to us. That's really kind of embedded in a lot of the polarimetric literature that's looked at supercells. It's we're basically just borrowing ideas from the tornado literature.
Okay, thanks a lot. I'll check that.
Yeah.
Thank you. We also have another verbal questions from Jeffrey Hoverson. Jeffrey, you're unmuted.
Yeah, hi, Jim. Really fabulous talk. I'm a colleague of Andy Miller's at UMBC, and I've looked at this case also kind of at the mesoscale aspects of it. And what I want to ask you about the May 27, 2018 is you've got the sense that there was echo training going on. In other words, was this kind of a multi-cell complex that got set up over that region, and there were, in fact, training cells with a genesis area and a dissipation area, in addition to the merger.
Yeah, I guess I have to say first that I start looking at all these from the Capital Weather Gang analyses. So I want to thank you for all your the great stuff you've done with the Capital Weather Gang. I think there is the idea of training is certainly part of what happens in both the May 27th, 2018 event and the May 15th, 2018 event in the Little Catoctin Creek, which I think you wrote about too, also wrote about that one. But there are other things that, this convective merger, this cell merger is kind of different from the typical training where you have cells forming, to the rear, they grow, they advect over the threat region. This is something over and above the sort of standard cell training, and it was kind of a surprising feature of the analyses to see two fully blown convective cells and in a 5-minute time period create this tremendous updraft structure. It really does harken back to things that that Joanne Simpson looked at, and that I think are important features of this storm. But we find signatures in multiple other cloudbursts as well.
Thanks, Jim.
Yeah.
Yes, thank you very much.
Great. We also have a number of text questions, which I'll read out loud. This first one is from Ralph Kahn. Severe convection events are often associated with extreme hail at the surface. Did the events discussed today produce exceptional hail? If not, what differences are there in temperature, structure, updraft, etc., between severe convective events producing extreme hail and those producing the greatest amounts of water?
Yeah, that's a good question. I'm not aware of any reports of hail at the surface for any of these events, and it probably works against some aspects of the extreme rainfall. There are certainly events where there have been, fabulous amounts of large hail and extreme rainfall in proximity. But here, what's common to multiple convective cells on May 27th, 2018, and other events is signatures of small hail with rain. And so it's these events, or these sort of microphysical mixtures that are, I think, particularly effective in producing the strong downdrafts that are that may well be a big part of the extreme rainfall story. Large hail would the drag contribution to negative buoyancy would be large, but what we've kind of systematically seen is more the signature of small hail with rain.
Thank you. This next question is from Dyla Zhang. She says, maybe I missed it, but it seemed like in one of your time series lightning figures, you only use the IC flashes. Is there a specific reason that you only used ICs, not the total lightning, ICs plus CGs?
Yeah. Yes. In looking at these events and kind of looking at some of the other literature, the IC flashes are more closely related to updraft structure, which was what we were trying to look at. So that's one side of it. Is it may be the case that the IC flashes are really more informative in terms of what we're looking at. We're not cloud to ground is really important if you're looking at hazards associated with ground strikes. That's not really of concern here. The other side is the IC flashes are kind of an order of magnitude larger than the cloud ground flashes for these events. And so when we look at the either the time series or the maps, they really wouldn't look any different if we included the cloud to ground strikes.
Thanks. So Anil Kumar asks, have you looked at the CAPE analysis for the Ellicott City floods?
Yes, the CAPE's large for both the May 27th, 2018 and the July 2016. They both kind of, at least in the NAR fields, they peak in the pre-storm period above 2,000 joules per kilogram. So there's plenty of CAPE for intense convection. There are actually relatively few events that are in our sort of 11 cloudbursts that don't have plenty of CAPE for intense convection.
Thanks. And this is my last question overall, but people can still send in their questions while they think of them. So this one's from Krista Peters-Lidard. She asks, what would it take for models like HRRR, i.e. WRF, to forecast these events? Resolution, microphysics?
Yeah, that's a really good question. Jeffrey's written about this and kind of inspired us to pursue the forecasting side. We've been working with Lucas Harris at the Geophysical Fluid Dynamics Laboratory and looking at short-term forecasting of these types of events. A lot of the capital weather gain stories really highlight the fact that these are just really, really difficult to predict. So what we're working with there is, it's not WRF, but the Geophysical Fluid Dynamics Laboratory model, which is the numerical core for the weather forecast system used by the National Weather Service. That's, we're starting that. I think it's one where I can't begin to give informed answers at this point.
Okay, thank you. I don't have any more questions. Does the audience have any questions to send me last minute? I can give it a 30 seconds. Okay, people are leaving, so I assume they're done. Well, thank you, Dr. Smith, for this great presentation, and thank you everybody else for attending and supporting our seminar series. This is the last one of the year, so happy holidays. We'll see all of you in January, end of January.
Thanks.
Thanks, Professor.